Hello, my name is Matt Personius, and the title of my presentation is Machine Learning for Heart Disease Prediction. I will be going through a machine learning prediction model for heart disease. Before I go any further, I want to let you know that I am not qualified to give medical advice, and this project is not medical advice. Please consult with your doctor regarding your individual heart conditions, and do not take this presentation as medical advice. So why did I choose heart disease for this project? Well, heart disease is the leading cause of death in men and women around the world and the United States. This table below outlines the number of deaths for leading causes of death in the United States between the years 2015 and 2020. I found my data set on the website kaggle.com. Kaggle is a great resource for data science competitions. They have a lot of data sets available for people to practice their data science skills on. So this is the data that I was able to download from kaggle.com. You can see that we have 918 patients, and this data frame shows age, sex, chest pain type, resting blood pressure, cholesterol, fasting blood sugar, resting electrocardiogram, max heart rate, exercise angina, old peak, ST slope, and heart disease classified as zeros and ones, 0 for no heart disease and 1 for yes heart disease. So these are the objectives of this presentation. First, I'll discuss why this prediction model could be beneficial for detecting heart disease in patients. I'll briefly explain how the model was created. I'll discuss the importance of cross-validation on this model. I'll deploy this model on unseen patient data. And lastly, we'll try to understand the features that positively and negatively impact the prediction model, and therefore understand what features people should be more conscientious of. So I'm going to go into the model here. I've built 2 models, or 4 actually, but on this page, this is a model for machine learning prediction on heart disease with no electrocardiogram analysis included. I wanted to make a model without the electrocardiogram analysis to see how accurate we could predict heart disease without having to put a patient through electrocardiogram analysis. The benefit of this is making this prediction in real time in a medical setting would be a pretty quick process. With the electrocardiogram analysis, that process is pretty brief, but sometimes it takes a couple days for that analysis to be completed and then put into a data frame. So just thinking creatively, this model could have a purpose in trying to make decisions quickly, and then the other model that has the electrocardiogram analysis would be able to provide a more accurate prediction. So the first thing I do is import the data, which was saved as a CSV file. And I cleaned the data up a little bit because we had missing cholesterol values. So wherever there were missing values, we replaced those with median cholesterol values. And I've dropped columns that have electrocardiogram analysis attributes in them. So ST slope, resting electrocardiogram, and old peak. The next step is creating category encoding for our categorical values or variables. So now, modeling with logistic regression, we can see that after running this model on our test data set, we have an accuracy of about 94%. And I just want to go back and touch on the model setup first. So I did a 80-20 split for the training and test split. So 80% of our data is used to create the model, and then we test 20%, and that's how we get our accuracy reading. And we can see the results of the prediction in this confusion matrix. So if you were to sum up these numbers, this would equal 20% of our 918 patient data set. So this is making predictions for each one of those patients, and then the confusion matrix is set up to show true positives, false negatives, and true negatives. So we want true positives and true negatives to be large numbers, and we want the false negatives and false positives to be smaller numbers. So looking at this scenario, having false negatives would be the worst case scenario, because this would represent a situation where we predicted that a patient did not have heart disease when they actually did have heart disease. So now I'll jump over to the model that has the electrocardiogram analysis, and you'll see it has a pretty similar setup. Same process of replacing missing values with the median, and same train and test split. And you can see when running the model, we have a better accuracy here, and especially there's less of our false negatives than there were in the other model. So 15 here and 8 here. And this model had an accuracy of about 91%. So I spoke briefly about the 80-20 split. And for people who are unfamiliar with machine learning, I'm going to go into a little bit of detail regarding why this is important and additional steps that we can take to improve the overall accuracy of this model. So imagine that these are 918 patients represented as data points. In the train and test split, our model will randomly select 20% of the data to be the test set. So this could be visualized as just being this 20% of data points here. So our model will consider all of the attributes of the 80% of patients represented outside of this circle, and it will just develop the model, and then eventually when it's time to run the model on the unseen or test data, it'll make predictions for each one of these points, whether or not they have heart disease. And because we know that this data point, say this data point we knew was a patient with heart disease, the model does not know that, and it predicts it, and then after the fact it checks whether or not it was correct. So one may wonder, well, what if the 20% that was selected has unintentional bias? And that's a very fair question to ask, and it does happen where the test set that is selected is easier on the model. Say that within this set here, there were patients who were very easy to identify as yes heart disease and no heart disease. So one way to work around this is to incorporate cross-validation. And so cross-validation will run the model on an 80-20 split, and then it'll choose a different portion of data to run the 80-20 split on. So just to visualize, our first time running, the 20% that was selected was over here, and then if we were to run it again, we could run it on this as our test data, and then we could run this section, this section. So whatever value we want to put in for the cross-validation number, that's how many times the model will run with a different set of test data. And this is really important because this helps eliminate any unintentional nested bias within the model. So when I first ran this model on without electrocardiogram analysis, you can see that we have about an 84% accuracy. But when including cross-validation, I've included cross-validation of 15 here. So the model will choose a different 20% for its test, the test portion of the model 15 times. And every time the model runs, it provides the accuracy scores. And eventually we're going to take the mean of all of those accuracy scores. So we can see that including cross-validation, this model has an accuracy of about 80%. Compared to just running it on the first portion of data, we originally thought that we had 84% accuracy. But then after including cross-validation, we have more confidence that the accuracy is actually closer to about 80%. Looking at the model that has electrocardiogram analysis, originally we found that the accuracy was about 91%, but then once including cross-validation with the same details as the previous Jupyter Notebook, we go through the same process and we are able to state that this model has an accuracy of about 84% as opposed to the 91%. So it's unfortunate that the accuracy goes down, but now this accuracy metric that we're providing is more accurate. And I do the same for calculating recall and precision, and I'll go into recall and precision a little bit more later on in this presentation. So I also go into a random forest model and go through the same process. So originally I had used a logistic regression model, and here I'm using a random forest model, and I go through the same exact steps, and I'm able to get the accuracy, recall, and precision metrics for this model. And I do the same for our data that has the electrocardiogram analysis, and here is the summary of the model. So I also run through some feature importance and partial dependence plots. This helps us identify which features within the data impact the decision-making process of our model. So in our Jupyter Notebook that does not have the electrocardiogram analysis within it, we can see that the maximum heart rate value carries a lot of weight in determining whether or not a patient has heart disease. And next in order would be age and then cholesterol. Later in this presentation, I'll go through a little more detail about partial dependence plots. But for right now, I'm going to run unseen data on our model. So imagine that the model has been accepted and it's now time to run this information or run this model on new patient data. So we have a patient and we're going to fill in, we're going to answer these questions. So what is the max heart rate of the patient? This patient has a maximum heart rate of 120. How old is the patient? 68. Patient. The resting blood pressure reading for the patient, 150. Cholesterol, 260. Is the patient here for exercise-induced angina? Yes. Fasting. Yes, 1. Here for asymptomatic chest pain. Okay, so now we've provided the inputs for this patient, and the model will make a prediction on whether or not this patient has heart disease. And while all of this is processing, eventually this could be put into a much nicer user interface. This could be developed into an application that could be used on an iPad. This is just a lot of the back-end work behind the scenes. So right now our model is taking the information that we've provided, and it's going to tell us the probability of whether or not this patient has heart disease. So according to this model, it is likely that this patient has heart disease, and the probability of this patient having heart disease is 99%. So the information associated with this patient indicated that there's a very strong probability that this patient has heart disease. And so in this case, it might not make sense for us to have an electrocardiogram analysis done or make a determination based off of electrocardiogram analysis. So at this point, someone could have a decision-making process based on the probability that we have here. If there was some sort of backlog in the electrocardiogram process, it would still be beneficial to have a better understanding of this individual patient situation. So I'm going to go through and run another patient, and eventually you'll see why I'm doing this. So max heart rate of the patient, 150. How old is the patient? 65. Female. Resting blood pressure, 150. Cholesterol reading, 200 or 220. Exercise-induced angina, no. Fasting blood sugar. And this patient has non-anginal pain. Okay, so our model will consider this new information and it'll make a prediction. Okay, so according to this model, it is unlikely that this patient has heart disease, and the probability of this patient having heart disease is about 26%. So probability could be determined, or like a threshold of value or prediction probability that could indicate whether or not electrocardiogram analysis should be completed. So let's say that the decision was made that this patient has an electrocardiogram analysis completed. So I will now run the model and consider the electrocardiogram details for this patient. So I will put the same information in that I put in the previous model, but now I'll include electrocardiogram analysis. So 150 for the max heart rate. How old is the patient? 65. Female. And on the previous model, I put 150. Cholesterol reading of 220. Not exercise-induced angina. 1. NAP. ST slope classification. So this would come from the electrocardiogram analysis, and for this patient, it is up and normal. Old peak value of 1. Okay, so I'm going to delete this, and now we'll process this information on the other model that includes the electrocardiogram analysis. Okay, so according to this model, it is unlikely that this patient has heart disease, and the probability is about 10%. So we were able to bring that down pretty significantly. So now I'll go into some further exploratory data analysis. So in creating this model and looking at some of the feature analysis, a couple of things that jumped out to me were age, maximum heart rate, and the electrocardiogram analysis. So there is quite a bit of research that's been done when looking at age versus maximum heart rate. And so you can see as we age, our maximum heart rate decreases in a linear trend. And so this shows the recommended maximum heart rate based on your age. And so what I found in looking at this data was, in general, patients with no heart disease had higher maximum heart rates. And so you can see this in the histogram. Red represents frequency of specific maximum heart rates in patients who did have heart disease, and then green represents maximum heart rate values in patients who did not have heart disease. So an important takeaway from this analysis is looking at model feature analysis and partial dependence plots. So these partial dependence plots can be interpreted by higher y-axis values represent higher probability of heart disease within the model. And so in looking at the scale of, or looking at maximum heart rate value of 100 versus 180, we can see that there is a smaller probability of a patient having heart disease as the maximum heart rate value is higher. And as we would anticipate, we can see how age has an effect on the model too. And then lastly, looking at partial dependence plot for cholesterol, I was interested in finding that cholesterol did not have as much of an effect on the model as maximum heart rate. And this was just an interesting observation for me because previously cholesterol was the one attribute that I tied to heart disease. And so it still does have an impact, but just not as much as I had previously anticipated. And so these were the two models. So the first model, no electrocardiogram analysis, and the other, yes, electrocardiogram analysis. In looking at the model prediction results, I used 15 as a cross-validation value, and these are the averages of after the fact. So we can see that we had better results in our random forest models than the logistic regression models, and we had better accuracy when including the electrocardiogram analysis. And then I just put this row here to show prediction runtime, assuming that it would take about a day for the electrocardiogram analysis to be processed. So this could serve a benefit in some scenario. And then looking at the other metrics of recall and precision. So recall highlights fewer false negatives, and precision highlights fewer false positives. So we really want to focus on eliminating false negatives. Again, that would be telling a patient that they do not have heart disease when they do have heart disease. So looking at this model, the yes electrocardiogram with random forest, we're able to have 87.7 for our recall percentage. And so now I'll go through some of the exploratory data analysis that I completed. So 918 total patients with and without heart disease. And this is just the frequency of patients with and without heart disease. This is the sex breakdown of our data set. So we had more males than females in our data set. And we had, respectively, more women without heart disease than with it, than men without it and with it. In looking at patient chest pain breakdown, so a lot of our patients had considered their chest pain type to be asymptomatic, and that was had the highest frequency within the data set. So we weren't able to tell too much from that feature. In looking at exercise angina is essentially exercise-induced chest pain. And we saw that most of the time when a patient did have exercise-induced angina, it was a strong indicator of heart disease. But with that being said, there were cases where patients did not have exercise angina and still had heart disease. So looking at general chest pain and exercise angina, this was something that I was trying to interpret. So we had a lot of patients who described their chest pain type as asymptomatic, who also had exercise-induced angina. So they must have answered, no, I do not have resting chest pain, but when I exercise, I do have chest pain, and that represents this right here. In looking at fasting blood sugar, so we did have a lot of patients that did not have high fasting blood sugar who did have heart disease, but then in patients who did have high fasting blood sugar, it was more likely that they would have heart disease than those who did not. Looking at the resting electrocardiogram analysis, so normal, if the result was normal, that had pretty little effect on the prediction. And then if the resting electrocardiogram analysis was labeled as ST, it was more likely that the patient had heart disease, and same for LVH. Another detail of the electrocardiogram analysis is the ST slope analysis, and this is really interesting to look at. We see that patients who have flat as the classification of their ST slope very strongly correlated to a patient having heart disease. Contrarily, in patients who have ST slope of up, we're more likely to not have heart disease. And I was not very familiar with ST slope, and I was able to find a resource that goes into this into a little further detail. If you're interested in reading through this, you can pause the video here, but I will not go through this. And then this was the distributions for all patients. So we have the patient age, maximum heart rate, and cholesterol levels. So this concludes my presentation. I appreciate you tuning in and listening to the information that I provided regarding my logistic regression and random forest models. And I hope that you're able to find some insightful information from this. And please do consult with your doctor regarding any conversation about heart disease. Thank you.